Okay, so while waiting for your friends, hopefully some of your friends will come to class today. Okay, if not, we just move on to cover new topic today. Okay, last topic for this chapter 7 on comparing three or more population means. Okay, means. Yeah, you can do the same thing for proportions. Yeah, proportions. Okay, but normally we start with means due to there's simplicity and widely used. Okay, than the proportions. Okay. Okay. By the way, I already uploaded the exercise. Okay. On this topic. Okay. So you can start looking at the question and then try to understand. Try to relate the question that I asked you to today's lecture. Yeah. See how you can solve the problem. Okay. So here, in this scenario, okay, we try to compare, okay, more than two populations. Okay, basically 3, 4, and more. Okay, 3, 4, and more. Right. So previously, from our previous work, we compare only two groups, right? Two populations, two samples from two populations. We sample them randomly. Okay, then we compare means. We can compare normally we compare by using the test hypothesis testing. Okay, same thing here. Okay, we do the same thing, but this time we will change the test statistic this time. Okay, and we will use the new test called the F test. Okay, which involves the variance. Okay, right here. That's why this new approach. Okay, this test is called ANOVA. ANOVA, okay, stands for analysis of variance. Okay. Okay. Right. And we will use the term treatment. Okay, for representing the groups, the populations that we want to sample. Okay, the terms treatments. Okay, so when I say treatments, just assume that it means the groups. Okay, groups. So we want to compare more than two groups. Okay, more than two groups. Okay. And let's look at the equation here. Okay. Okay. So first. Yeah. Okay. So let's say in this case again, we still want to compare the means. Okay. The population means. So we use mu. Okay. mu1, mu2, mu3, mu4, and up to certain number of treatments or groups. Okay. And then we set up the hypothesis. Okay. Like this. Okay. H of 0, H subscript 0. Okay. We assume that all means from 2 or more, 3 or more populations are equal. Okay. And we use this one here, the alternative hypothesis, right? Setting it as at least 2 of the K treatment, at least 2 K means differ. Okay, what do we mean by at least two? At least two. That means could be this two, right? They are not the same. They differ. Or it could be this and that. Or this and that. Doesn't matter which two. Doesn't matter. Okay. Could be this group and that group. It's still okay. It could be more than two, right? Could be this group, and that group. On and on. It doesn't matter. At least two groups differ in terms of the means. Okay. You will see example later on to better understand this. Okay. So, right. So this is the hierarchy of the populations, the sample, and the groups. Okay, within the samples. Okay. So basically, here we have the population of the experiments. Okay, populations. Okay, it could be different populations. Okay, different populations. Okay. Okay, and here we have the sample. Okay, sample from the population. Okay, that would be used to represent the population, and then in more details, we will have different samples, okay, from different groups. Okay, here we have here from group 1, group 2, group 3, on and on, until let's say K. There, okay. So we call each group here treatment. Okay. Now, okay. So in this analysis of variance ANOVA, we need to compute sum of square. Okay. Sum of squares for treatments and sum of squares for error. Okay. For treatments, okay, sum of squares. Here you see the summation, right? That's why it's called sum. Sum of summation of what? Of squares. You see square there. Okay. Square of what? Of the difference between x bar. X bar here represents the whole populations. Okay. Average, the mean, right? So basically, yeah. Okay, let me try to write like this. Okay, so basically you have population. Let's say assume, okay, for example, n equal, let's say 100. Okay, 100. Okay, and then you want to split into somehow, okay, into treatments. Okay, here you have here treatment. Group 1 treatment, 1 treatment, 2, and then treatment 3. Basically, this is a group, right? Group. Another group. Okay, this is the statistical term. And then here the size. Okay, you have here n1, n2, n3. The size, when you sum all the size, it should be total to n, right? So here, let's say, assume normally the size can vary, can differ, but it would be nice if you try to now spread them equally. Yeah, it would be good, right? So more or less, this could be about what? 33, 33, right? So adding up to 100. Okay. Now, so now here you have for this one. Okay, you compute the mean for this one here. Okay. And then here would be x1 bar, x2 bar, x3 bar. Okay, the mean for each group. Okay, the mean, the average. Okay, and also you have this guy here, x bar. X bar is the mean of this guy here, 100. When you add them all, right, you compute the mean. And if we use x bar, okay, this is x bar there. Okay, that's what I mean. Okay, and the x sub I bar is the average, the mean for each treatment group. Okay, so basically here you do something like this, right? So you sum, okay, summation of the differences between the whole population and for each group square, and then you multiply each square by the size. Okay, you know, right? So n sub I is this guy here. Okay, right? N sub I, n sub 1, n sub 2, n sub 3 subscript. Okay, and then you will get this guy here, k. What is k here? K is the number of groups, right? So here k equals 1, k equals 2, k equals 3. So basically here I runs from 1 to 3 groups. You want to compare 3 groups, right? In practice you can compare 4 groups, 5 groups, doesn't matter. Okay, 3 or more. Actually 2 would be okay. You can still use this ANOVA. Okay, this ANOVA here. Okay, to this ANOVA, right? To compare between 2 populations. It still works. Just like previous approach that we learned. Okay, we can still use this approach, but normally we reserve or we tend to use ANOVA for 3 or more groups. Okay, like this. Okay, so that's it, right? So this is the first thing that you need to calculate, compute. So another thing is sum of squares for error. Okay, for error. Okay, so what we mean by errors is the differences within each group. Okay, here each group. Right. So based on this example, we have 3 groups. K equals 3. Okay. And here, so for each one of these, you have here the set. Okay. x1i, x2i plus 1. Something like that. No, I'm sorry. It should be x1 still. Okay, same group, right? x1 I plus 1. Okay, x1 I plus 2, on and on. Okay, up to this size. Okay, same thing here. You have x2 I plus 1, x2 I plus 3, on and on. Okay, for this group. Same thing for this group, right? x3i plus 1, on and on. Okay, right? So for the errors, sum up squares for the errors here. So you sum again, summation. Okay, summation, right? Summation. Okay, within each group you do this one. Okay, within each group, right? This is second group, third group, up to what? Up to k groups. So there we have 3 groups, right? So for each group, you simply compute the differences and then square. Okay. And using this formula, x1j, just like in the case, each element in each group. Same here, x2j for second group, each element. Okay, same thing, on and on. Okay, and then you see here x sub 1 bar is the average of that group, which is this guy. Okay, not this. This is everything. This one. So basically, you subtract each one of these, right, to x1 bar. Okay, x1 bar. For this group, subtract each element by x2 bar, and then square. Okay, and that's it. And then, by the way, okay, this equation, okay, is the same thing as this one here. Okay, using the square like this, okay, if you can recall it, you will see that this equation is related to variance, okay, and we can use variance here. S square stands for variance. Okay, that's why you get this name here, variance. Okay, right. So this equation, right, can be rewritten in these forms. Okay, in terms of variance, simply multiply, okay, n, okay, the size -1 to variance. Okay, you know why? Because to say this is a variant, right? So your variance is like this: summation of xi minus x bar minus n minus 1, right? So you simply move this one to this side, you get this guy, and then this side, you see this new ways to write the equation. Okay, from that formula that we learned in previous chapters. Okay, the variance. This is a variance. Okay, a variance. Okay, now so now we have two values now. Okay, sum of square for treatments. Okay, one thing we use SST. Okay, and another one is sum of squares for errors. Okay, like this. Okay, now move on, and then we need to normalize. Okay, make it regular somehow. Okay, we simply need to divide those sums, okay, by the size. Okay, so for treatments, we need to divide the sum by treatment, the number of treatments -1. Similar concept to this guy, right? -1. Yeah, just the way it works. So here we have 3 treatments. K equals 3, right? So you need to divide the sum by 2. 3 minus 1 would be 2, right? This guy. Okay. And for the errors, again, you need to divide the sum by n minus k. N minus k. Why? You know why? Because this is for every items, every elements. Okay, and then each element you need to subtract. Okay, basically what? Each group, right? Each group. For example, here, each group 1, group 2, group 3. You subtract by n minus 1, n minus 1, n minus 1. Okay. So the total is n1 plus n2 plus n3 minus 1 minus 1 minus 1. And this guy would be n, right? This one would be k. That's why you see this number here, n minus k. Okay, right. So because we combine, right? We combine the summation like this one, right here. This is n minus 1, n1 minus 1, n2 minus 1, n3 minus 1, on and on. Okay, so eventually this one would be n minus k. Okay, that's how you obtain this denominators. Okay. Now we are ready to set up the test for ANOVA. Okay, and the test. Okay, no worry about this. Okay, just show you the works. Okay, and the test is called the F test. F test. This is a new terms, new equations. Okay, for you. Okay, right? And the F test is simply equal to this number over this number. Okay. In the exam, no need to memorize the formula. I will give you this time. Okay, everything. Just know how to use it. That's enough. Okay. Okay, and this is called the F test. So we call this one F test. Okay, F test. And then we need to have another kind of distribution table. Okay. Okay. And the table. Can you see the table? You see that this is called the F distribution. Okay. The table looks like this guy here. If you look at your online materials, okay, on your class website, I posted the link here. The last item here, the link for the F distribution table. Okay, just click on that link. If you click on this link, you see something like this. Okay, so we borrow these tables from these universities somehow. Okay, doesn't matter. Legally, you can use this. Okay, this is a F distribution table. And then you can select the alpha values. The alpha value 0.1. 0.1 is what? 10%. 0.05, 5%. On and on. Okay. Okay, and then you see the scroll down to see the table. It looks like this. Right, look like this one here. Can you see the shape here? Shape. Okay. And you see here DF1, DF2. DF stand for degrees of freedom. Degrees of freedom, just like the T test. Okay, the F test has two variables. Okay, here DF1 on the row, DF2 in the column. Okay, and this one is just for the alpha equals 0.1. So you see something like this. I will show you how to use this table soon. Okay, later. Okay, but this is how it works here. Okay, right. So now come back to this guy. Okay, so right. So now we can set up the hypothesis now. Okay, we want to test if 3 or more groups or treatments differ in terms of the means or not. Okay, we set up something like this, right? So by default, we set them to be equals, just like previous setting that we have learned so far, right? And for the alternative, we just simply say that at least two, could be 3, 4, 5, 6, up to k, doesn't matter. At least 2 of the treatments differ in terms of the mean. Okay, means differ. Okay. Now then we need to use the statistic, the test. Okay. And this time again we call this the F test. Okay, this equation MST over MSE. And to compute this, just go back to the previous slides. Just see how you can compute that. Okay, basically very easy. Okay, and then similar concept to previous approaches. When you want to reject or not to reject, right? We need to compute the area called the rejection region. Okay, using the new test like this. Okay, if the values falls within the region, then you can reject the now, reject this guy now, and keep the alternative. Okay. right? So very simple. Okay, but you need to look up the table. Just show you there. Okay, and then you need to use degree of freedoms here, V1 and V2, or the F1 or the F2. Okay, the F1 or V1 is equal to K minus 1, treatments minus 1. Okay, the F2 or V2 is equal to N minus K. Okay, and that's it. Okay, simple. Okay, let's try to look at example now. Okay. By the way, before doing that, okay, these are conditions that you need to be concerned. Okay, before you can use that test, you have to be sure that the sample here, right, that you select must be done randomly. Okay, randomly selected in an independent manners, independently. Okay, right, when you sample, let's say I have here 100 students. Okay, I want to split them into 3 groups. Okay, I split them into, randomly select them into 3 groups, and then I compute the average, and so on. Okay. Second condition is that all K sample populations, okay, have distributions that are approximately normal. Okay, basically, let's say this group, right, come from the normal distribution population. Same here, same there. Okay, this condition is the same thing as our previous assumptions. Okay, about the normal distribution. Okay, because we don't know if the size is small or not. Okay, here the size could be smaller than 30. Okay, it doesn't matter. We can still use this formula. So this formula here, ANOVA F test, can handle both large sample size and small sample size. It doesn't matter. Okay, so we have to assume that the sample populations are normal or are approximately normal. Okay, and the last condition that we need to assume or have is that the populations, okay, for the variance, for each group here, the variance must be approximately equal. Should be more or less the same. Okay, right? So it doesn't have to be exactly equal, but should be close enough. Okay, that's good enough. Okay. Okay. So if you have all these conditions, you can use this test, okay, to compare. Okay. Now, okay, like this. Okay. So now let's look at the example now. Example about 4 brands of golf balls. I don't know if you play golf or not. Okay, I don't play. Okay, but I can watch the golf. Okay, let's say there. Okay, in the US. Okay, it compares the driving distance. Yeah, how far the golf balls could travel or could go after being hit by some ions, some stick. Okay, how fast each ball goes might depend on the brand. Okay, different brands, right, may have different qualities of the balls. I don't know. Okay, from the materials. So they want to compare the mean driving distance. This means when you drive, when you hit the balls, right, it can go very far away. So you compute the means for each brand. Let's say you have 4 brands. I don't know, Nike brand, for example, Adidas, and so on. Okay, you compare. Okay, so now you want to see if there is any difference in terms of the means of the driving distance of the golf balls. Yeah, for those 4 brands. Okay, brand 1, brand 2, brand 3, brand number 4. Okay, so we set up the hypothesis. All are the same, equal, the default one. Okay, the alternative, we said that at least 2 of the brands differs, at least 2, could be 3, could be 4, all 4 could differ. It is still okay, but we just want to get at least one pair. That's enough. Okay, so at least 2 of the brands differ. Okay, and then we have here, we have confidence levels. Okay, when you want to test something, you want to say that, okay, I would like to have this much confidence in saying that, saying this, right? So normally this is given, the alpha, right? So the alpha is 0.1. Alpha 0.1 means 10%. So the confidence level is 90%. Okay, 100 minus alpha would be enough. That confidence levels 10%, right? So would be 0.9 confidence levels, the alpha. Okay, now you set up the F test. Okay. Okay, by the way, do we care about 2 tails, 1 tails here? No. Because, okay, even though this is an equal sign, could be what? Could be unequal. Could be less than, could be larger than, we don't know. So we don't care about 1 tail or 2 tails for this test. For this test, we don't care, okay? The F test, we don't care. Okay, we simply use this value here, the given alpha, and then compute this guy, the mean. Okay, mean sum of square for treatment, mean sum of square for errors, something like that. Okay, compute. Okay, and rejection region 2.25. How do you get this number here? I will show you it from the table. Okay, so let's see. Okay, here you have here V1. What is V1? V1 is the degree of freedom. F1, which is what? K minus 1. Okay, so if you come back here. Here, okay, V1, this guy, okay, V1 is K minus 1, dF1, okay, V2 here, A minus K, okay, you need to know this, okay, yeah, okay, V1 and V2, okay, now, so to compute this guy here, to compute this rejection of region, you need to use a table, okay, in the table you need to use 0.1 alpha, okay, along with V1, V2. V1 is K minus 1. K is 4, right? Minus 1 is 3. So basically 3. V2 is N minus K. N is total number of balls. How many balls total? 40 balls. Okay. 40 balls. Okay. It did not say there, but from let me see. Okay, not there. The total number of balls are 40. Okay, 40. Okay, it doesn't say that. Okay, but 40. Okay, 40 minus K is 4, right? So you get 36 to be V2. Okay, right here, right? About 40 golf balls. Okay, 40 minus K. Okay, now you have this guy here. Okay, V1, V2, right? And in alpha 0.1. So to get this number, let's see, 2.25. So go back to the table. Okay, from here, right? So again, from this link, click on this link. You see this table. Okay, and then here you click on point 1. Here, okay, point 1. Point 1, okay. And V1, what is V1? The F1, the same thing as V1. V1 is 3. This column now, okay. And what about V2? Okay, the F2. V2 is 36, right? So 40 minus 4 is 36. So you keep scrolling down to 36. Let's see. So, okay. This one, right? 1, 2, 3, okay? 3. Scroll down to 36. And where? It's somewhere here. If you scroll down, and then you see the value here. 36 somewhere between 1 to this guy, right? Right? In the table, you have only up to 30 and 40. No such value in between. We have 36, right? So you can approximate yourself, right? 30 this much, okay? So 40 is this much, okay? So it's about, the difference is about 10, okay? So your 36 or 35 should be somewhere in between this and that, okay? Then you approximate, okay? Table is not given. I mean the value is not given, but you can approximate logically from here and there. So it should be somewhere between this and that. So the answer is 2.25 here. Okay. Between 2.23 and 2.27 should be 2.25. Exactly, right? So your value there is 2.25 there. Okay. And then you compute the F test. Okay, here. So you compute, okay, there, right? So these are the summary here, right? 4 bands, 40 golf balls. You want to compare the means, okay, here, okay, degree of freedoms, V1, V2, okay, sum of square. You need to do that yourself, okay. Okay, assume we are given like this. Sum of square, okay, mean square, F test, okay. So you set up F test, and then let's say your F test is this guy here. When you set up the formula, you get, okay, this one, okay, 43.99, and then what is your conclusion? From the table, right? The F score is 2.25, but the one that you receive from your sample is 43.99. It's much larger than 2.25. So what happened? So it falls in the rejection region. Okay, so right. So basically you reject, right? Reject the null. Okay, reject the null. Here, right? So we reject the null just like your previous work. Okay, and that's it. Okay. Question? Okay. Now your work next is to do this. You need to compute this one for me here. You need to compute this for me. Okay, as your exercise. Okay. These are givens, but your today's exercise, this one, Okay, and it is the last one for this chapter. Okay, so basically this chapter, okay, I skip some topics. Okay, right. So that's all I need to cover for this chapter. This is the last topic for this chapter. ANOVA. Okay. So whichever topics that I don't cover or I have not covered in classes, I will not ask you in the exams. Okay. So before the exam, we will come back here again and review all the topics that I will ask you in the exam. Okay. To be fair. Okay. Now. And this is your today's exercise here in class number 21. Yeah. Okay. Okay, this is about the facial expressions. Okay, so when you express something, right, or through your face, okay, someone can perceive you as angry or happy or sad or neutral, nothing. Okay, so basically there are some experiments about the facial expressions. Okay, done back in 1996. Okay, and the sample size is 36. So there were 36 students, 36 psychology students. Okay, psychology students. Okay, so took part in this experiment. Okay, and so the experiment involves looking at the images, okay, images of people or slides of people having different expressions. Okay, and ask each student to rate the score. Okay, based on the scale from minus 15 to plus 15. So these are scores. Okay. Okay. So here we have 4 groups here: angry, disgusted, fearful, happy, sad, and neutrals. Okay. So question 1 to know if there is any difference in terms of the scores. It's called the dominant score. The dominant score. Whatever score here. Okay. Okay. Right. So 1, 2, 3, 4, 5, 6. Right. And 6. And each one has 6 students. Right. Right here. So basically here, into 6 groups. Okay. Student was randomly divided into 6 groups. Okay, equally. Okay. Each group was assigned to view one of the 6 slides showing facial expressions. Okay, like this. Okay. So now your K, the number of treatment is 6. Right? K equals 6. Okay. And N, the total size is 36, right? So your degrees of freedom, V1, V2 is K minus 1, which is 5 for V1. V2 is N minus K. 36 minus 6 would be 30, right? So 5, 30 would be V1, V2. And you use the table at the alpha equals 0.1, the same table that we just saw. Yeah, and that's it. Okay, and right here. So question asks you here, conduct an analysis of variance ANOVA F-test to determine whether the mean dominance ratings, this scores, differ among the 6 facial expressions. Okay. So this is your exercise today. So you need to set up now hypothesis, alternative hypothesis, F-test. You need to compute this. Okay. You need to use calculators. You can use your calculator on your smartphones. Okay. Okay. The TA, she needs to go for proctoring another exams. Okay. So you need to submit your exercise to me today. Okay. Today. Okay. Oh, by the way, Ajahn Dr. Narongrit asked me to mention this to you. Okay. This afternoon, starting at 2 p.m., he will have his data structure class. He will lecture the data structure class. 2 classes today. Okay, 2 consecutive classes, starting from 2 o'clock, right, until I don't know, until 5 something. Right, 2 classes today. He said. Okay. So if you take his class, data structure, you need to come to class at 2 p.m. Okay. Tell your friends too. Okay. Okay. And now, right here. So. Question? Okay, making sure that you submit all the assignment and homeworks, exercises, okay? Just in case you did not do well in, or you don't do well in midterm exam and final exam, so I can help you, okay? Using the homeworks, assignment or marks, okay, to give you some credits. Otherwise, you might fail the course. Okay, so make sure that you submit everything that I ask you, and do it. Try to understand this. So here for this assignment, right? For this exercise, okay, you do something like this. So this is ANOVA F-test. Okay, for 3 or more population or groups, or treatments. Okay, just like in this case, right, we have 6 groups. We want to compare the means, right? So you set up the now H subscript 0, H alternative. You can say that mu1 equals mu2, mu3, mu4, mu5, mu6, right? Okay, that's it. That's you're done. Okay, and alternative. At least, you said, at least 2. At least 2. Could be 3, 4, 5, 6. We don't know, right? At least 2 treatment. We call this treatments. Okay, we call it treatments. Okay. Differ in terms of the means. Okay, right? But you need to say that mu1 is the mean for angry. Okay. mu2 for disgusted. mu3 is for fearful. So on. Okay, like that. Okay. And what is n? N equals 36. K equals K's treatments. 6, right? So V1. So your V1, V2 is K minus 1, which is 5. V2 is N minus K, which is 30. Okay, and alpha is given as 0.10, 0.1. Okay, so you know pretty much everything now. Okay. What else do we need to know? Huh? From this question here, you need to make assumption, right, about the normal distribution. Okay, about the equal variance. Okay. Okay, so you make some assumption. Okay. Equal variance, normal distributions, random samples, 3 assumptions. Okay, now your next task is to compute the F test. Okay, like this. So compute the F test, okay? F test, F score, okay? F score, F test, that's a mere. Let's call this score. Equals MS, what? MST, right? MST over MSE. Okay, I try to memorize here this. Okay, MST over MSE. Okay, and MST equals so it's MST. Okay, you need to do this one by one. Okay, MST equal what? MST equals not M anymore. SST over K minus 1. Okay, MSE equals sum of square for errors over N minus K. Okay, right? So okay, try to do something like this. Try to follow this logic. Okay, and then try to look up the formula from on your slides. So now you know this guy already. You know this. You don't know this guy and this guy. So your next task is to compute SST and SSE. Now this involve using the calculators now. Okay. And this one is equal to summation of. Alright, okay. Can you tell me? And I don't know, whatever. I equal 1 to K. K is what? K is 6, right? Okay. 1 to 6. N sub I times X. Okay, right? X bar minus xi square. Okay? Am I right? Double check this for me. Just in case I forgot, yeah, I make some mistake. Okay? Hopefully it's correct. Okay? This is the mean for everything. For the whole thing here, you sum them up. Oh, that's a lot. But you use calculators to be okay. We don't use R programming now. Okay, it's too much. We don't have computers, so you can use Excel. You can use calculators. Find the means. Okay. This is X. Okay, and this guy is equal to sum of square errors. Sum of square for errors, which is equal to N, the the short formula. Oh, you want the summation? Oh, okay. Summation of what? Okay, you can use this one. N. Oh. Summation of I from 1 to k, right? Okay. And n sub I. Is that right? Oh, to n. Are you sure? Okay, let me check this one. This one will be S. I try to use this guy. S. Oh. This S would be the whole thing. Right? This S. I. Is that right? Yeah. Let me check. So, something like that, okay. Let's check. To make sure. Okay. This guy. This is what we want here. This, again, I will give you in the exams. Okay. So, check this for me. This one. Is this correct? Seem okay, okay. SSE. I try to use this one. Okay, don't worry about this, it's too much. Okay, try to use this short, yeah, better. So, okay, so A-1, okay. So I should use A-1 there. So try to use this, is better, faster. Okay, so Ni minus 1 time. Ah, okay. Sorry. This is mistake here. Mistake. And S I square. Okay, that's right. Yeah. Ni Si N2 S2. Okay, that's it, right? Up to K. Is it better? Okay. Right. And that's it. You're done. And then you compute the F score. And then you use the table. Open at the table. And then answer that. Case. Some square for error here, right? This is up to k. That's why I use k there. Okay, but not this one. I use this one here, okay? Okay. And this is up to k too. So very similar here, right? Except Ni minus 1. Change this one to be S. Oh, not that bad. Okay. And then your question is right here, okay? That's it. Any more question? Okay, now you need to compute. You need to compute what? You sum all of this. Compute X bar for me. Okay. So you add this to this, okay? Divided by 36. That would be X bar. Okay. And then you compute Xi bar for each one. Each one. Okay. And then you can solve this one already. You know how to solve this. Okay. Then you need to compute S square for each one of these. The variance. The formula for the variance is, you know, right? Yeah. The formula is summation of Fi minus X bar, okay? N minus 1. I equals 1 to N. Okay, this is a variant. Okay, like that. Right. So that's why in the exam, in the final exam, I will ask you to bring in calculator because we need to punch in numbers. Okay, it's too much to do it by hands. No need to. Okay, still have time. Yeah, you can stay here until noon and submit it to me. Okay, put it there. I will collect after the class. Okay, so I will see you again next 2 weeks. Yeah. Second next Wednesday. 19. Yeah. 19th of April. And then after that we have only 3 weeks left. Or 2 weeks left. Not many. 2 weeks. 2 or 3 weeks, yeah. So I will cover only one topic for the next chapter 8. Only one topic about chi-square, and then I will move on to last chapter 9, on the regressions, linear regression, and that's it. And then we will do reviews for the final exams. Okay. We have chapter 5, 6, 7, 8, and 9. 5 chapters. That's a lot. That's why I try to cover only some important stuff. Not everything. It's too much, I know. Because so I want to cover only things that you will use in the future, in your future study, in your projects in the future. So I don't want to cover everything that it could be useless. Okay. But we need to know something. Okay. Hopefully, out of this class or this course, when you walk out at the end of the semester, you know something about samples, about populations, about F-test, about T-test, about C-score, C-test, about hypothesis. That's enough for me. I am already happy if you know that. Okay, it will be good. Okay, so you can talk to someone else about this, and then they understand what you means. That would be good enough, Okay, for this course. And some of you may travel this coming week. Okay, so again, try to stay safe. Okay, because there could be some accidents on roads, car accidents, a lot. So try to avoid some dangerous places.